Okay, here we have a planet, in this case Earth, and this is a gravitational field pattern around it. This is known as a radial field because it's pointing toward the center along the radius. So a gravitational field or radial field appears around planets, stars, and other large masses, which can be treated as point objects. So they can be treated as a particle and acts toward the center of the particle. And it points in the direction a mass would experience a force. So, and it points toward the center of the planet. So in this case, if I put a mass there, it would experience a force toward the center like that. Now, doesn't just because it experiences a force in that direction doesn't mean it will necessarily move in that direction. It would accelerate in that direction, but if it has a velocity in some other direction already, then it might follow that path while accelerating toward the center. So, for example, a path like this. And at any other point along that path, if you draw the object there, then the force again is in the direction of the field lines. Okay, so the direction of the field lines point inwards because the force will always be inwards toward the center. Okay, and the closeness of these lines indicates the strength of the field. So as you can see at the very bottom right corner here, the number of lines in this square box is just one line. But if you get closer towards the surface, there are more lines in a unit area. So that means that the gravitational field is getting stronger the closer you get towards center. The gravitational field strengths are stronger closer to the surface, and that is shown by the closeness of the lines. Okay, another important definition is the gravitational field strength, which is defined as a force per unit mass on a small test mass placed in the field. A small test mass because if it had been another huge planet, then obviously that's going to change the gravitational field at that point. So gravitational field strength is a force per unit mass. So given this equation, force divided by mass, G here is the gravitational field strength in newtons per kilogram. F is a force in newtons, and M is mass in kilogram. And we know an example of gravitational field strength on the surface of Earth is minus 9.81 newtons per kilogram. And a lot of the time you use the acceleration. That's because when there are no other forces, 9.81 will be the acceleration due to gravity. But if you move further away from the planet, and that's what we're going to start doing now, the gravitational field strength is going to get weaker. Okay, as you can see, the lines are getting further apart. And if you get even further away, then it gets weaker. So in this top left corner here, it's 5 newtons per kilogram on any mass placed there. Okay, so let's put a mass there. Actually, let's put a 300 kilogram like asteroid over there, and let's calculate the force on this mass. So force is going to equal mg, just like before, but we're not going to use 9.81 from now on. We're going to use based on where we are inside the gravitational field. So at this point, that mass on the top left there is at a gravitational field strength of 5 newtons per kilogram. So we take his mass times it by the gravitational field strength, and that gives us a force of 1,500 newtons on that mass at that point, and that force is going to be pointing towards center. Obviously, if you had been closer to the surface, the weight of the object would have been bigger. And the acceleration of that object is going to be towards center. Again, doesn't mean it will move towards center. It could be going around the planet, for example. We're going to start zooming in to that radial field. If we zoom in enough, it becomes a field pattern like this over small ranges. This is called a uniform field or uniform gravitational field in this case. So over small distances and long flat surfaces, it looks a bit like this. As you can see, it still points in the direction of the force. So it's still pointing towards the center of the planet in this case. And the closeness of the line still indicates the strength of the field. But if we go over small enough region like this, actually the lines are basically parallel and the distance between them are equal. So in this case, the gravitational field strength is actually pretty constant. And this is what we've been dealing with in year 12. So the gravitational field strength here would have been 9.81, here would have been 9.81, and here 9.81. So that's because you can see the lines all equal distance apart, and the gravitational field strength is pretty constant across this small height. So on the surface of Earth, this could be a couple of kilometers before it's actually getting weaker. There is an exception to this, so let's pretend there's a region here where the ground is made of very heavy elements. Okay, so I don't know, lead or something like that. In this case, the gravitational field pattern does change ever so slightly. We'd have to add these few lines here. So as you can see, there are more lines just above the ground with the dense elements, and also the lines are bending towards it a bit. So if a person was walking over here, the gravitational field strength on the far left here is still 9.81 because you can see the distance between the lines hasn't changed. And let's say their weight was 600 newtons. But as they approach closer to this region with very higher gravitational field strength, it's not going to be that much stronger actually. Okay, then now maybe the gravitational field strength is 9.82 instead of 9.81, and these small variations can occur on the surface of the Earth. Not only that, the mass would have increased ever so, the weight would have increased ever so slightly. Sorry, the mass would not change. And even more importantly, the force wouldn't be directly downwards, it'd be pulling them towards the ground with the denser elements inside it. Okay, and when they're walking away, it'd be the other way around. It would be pulling them back towards the ground with dense elements. So that means when they're walking um, towards the ground, then they would have been actually pulled, almost accelerated horizontally towards it as well. And when they're walking away from it, they'll actually be pulled back, so they'll be decelerated uh, towards the left. This is also true with mountain ranges. They can, if they're really big mass, because gravity is produced by these masses, huge masses, they could also bend the gravitational field strength, field pattern around them and attract objects towards them.